We are in the week 2 problem solving session of the NPTEL course Network Analysis, and week 2 is about a deeper look into energy storing elements, which are inductor and capacitor. I am Teja Golla, a third year research scholar at IIT KGP. Let me share my screen. Let me know when you can see my screen. Hello, can you see my screen?
Yes, sir.
Okay. So before we go into the week 2, I would like to revise what we have covered in week 1. So let me just go back to week 1 and week 1 notes. Okay. So in week 1, we have started with the mesh analysis. So we have discussed how to write the equations using mesh analysis. We have considered this example and we have written 3 equations, and then we discussed that we can solve these 3 equations to get the 3 unknowns, and later, depending upon the question that they have asked, we can find any value, any voltage or any power dissipated in any element. Then we have discussed about the nodal analysis. We have taken one example, and then we have understood the KCL and how to write the KCL. So initially we have discussed about how to select the direction of the current in all the branches, and after selecting the direction, then following that convention, we have realized that we need to follow that convention, and we have to write the equations. Then we have written the equations, and then we got 3 equations and 3 unknowns. Then we went to a problem solving session where we have considered one problem, and after considering that problem, we have realized that we cannot directly apply nodal analysis. So we went to some other equation, and then we got from that other equation this third equation. We got this third equation from the other node. We went to other node and we got the third equation. So after getting the third equation, then we got 3 equations, 3 unknowns, and we have solved the 3 equations, 3 unknowns. Then some few people had queries regarding whether we need to choose any reference ground, or how it will affect if I select any other reference ground, and then I have selected that. Depending upon the reference, our potential will vary, but the potential difference between any 2 points should remain same. So that we have proved by considering 2 different reference points. And then another person has asked like, if he or she takes a different current convention in the beginning, will that be affecting the this answer? So I have taken 2 different scenarios where I have considered 2 different current directions, and then I came to conclusion that I have proved that it does not matter. We will be getting the same result irrespective of the current direction that we assume at the beginning before solving the problem. Then there were a few queries regarding why not to short to uh, voltage sources, and why we should not connect to current sources. So we have discussed that in one case KVL will be failing, in the other case KCL will be failing. So this is all about the last week session. So before going into week 2, I would like to again discuss about this mesh analysis. I wanted to again like just revise this Supermesh and Supernode. I have not specifically mentioned Supernode last week, so I want to just quickly cover this Supermesh and Supernode. So I hope you are able to see my screen. Hello.
Sir, today please cover energy and power related problems.
Okay, in LC or related to last week, this week, right?
No, this week.
Hello, week 2, right?
Week 2, yeah.
Okay,
Yes,
okay.
oh, sir, week 2, sir.
Sorry, week 2.
Sir, week 2, sir.
Okay,
Yes,
okay.
sir.
Okay, okay. So
In the
just
RL circuit, RC circuit, and RL circuit.
okay, okay. So just give me a few minutes time. I would like to revise Supermesh and Supernode. Then we'll go to the problem solving. If you have no queries in the concept, then we'll directly go to problem solving. Then we will solve few problems. Is that okay with you?
Yes, sir. No problem with Supermesh Supernode.
Okay, so I'll just quickly cover this and then we'll go there.
Yes, sir.
Okay. So first I'm considering Supermesh. So Supermesh is a case where a current source is being shared between two meshes. So let me consider one example. So if I take say some 2 volts, 5 volt, 1 ohm and 2 ohm and say this is some 3 amperes. So in this case, what happens is say I have selected, sorry, someone trying to say something. Okay. So say I have considered the clockwise direction of the currents I1 and I2. So from this I1 and I2, I can see that I1 minus I2. So in this branch, I1 is flowing like this and I2 is flowing like this. So as the current is flowing toward downward direction, so the downward current is given by I1 minus I2. So I1 minus I2 will be 3. So this is equation 1. So for getting equation 2, we consider supermesh. So what supermesh is by uh, from the given circuit, if we remove the current source between those two terminals and apply KVL in the remaining mesh, then that is called supermesh. So here, what we'll be doing is we'll cut these two nodes and we'll draw the remaining circuit. And from the remaining circuit, whatever we'll be getting, we'll apply KVL there. So this is one resistor and this is another resistor. These are the two sources. And here we have disconnected that, so there is no point of considering that. So now if we apply KVL directly here, so this is 2 volt, this is 1 ohm. So I1 is flowing in this part and I2 is flowing in this way. So 2 ohms and this is 5 volt. So if I apply KVL over here, what I will be getting? So if I say I started from here, so it will be plus 2 minus 1 into I1 plus 2 into I2 minus 5 is equals to 0. So this is my equation 2. So one equation I got directly from whatever current source they have provided. So this equation is coming from the current source, whatever they have given. And this is coming from Supermesh. Supermesh is the mesh that is left when you have removed the current source that is being shared among two meshes. So whatever current source, let me admit all the story. If someone is trying to speak something, I'm not able to hear, you can mention in the chat box. Your voice is breaking. If you are not trying to speak, then kindly mute yourself and yeah.
So it should be minus 2I2, I think. So.
Yeah, sorry, you are right. Let me run this. Yes, you are right. It will be minus 12. Yeah, you are right. So this will be minus. So by solving these two equations, we'll get the two unknowns which are I1 and I2. So this entire thing is called super mesh, where we got the outer mesh by neglecting the current source. Now, if we go to supernode, so these are like if a current source is there between like a shade in between two meshes, then K mesh analysis cannot be applied. And if a voltage source is directly connected between two nodes, then we cannot directly apply the nodal analysis. So these two are analogous to each other. Here it is shared between two meshes. In that case, it is in between two nodes. Here it is mesh, there it is node. So like these two are analogous to each other. One is current and another one is voltage source. So let me consider supernode. In the case of supernode, let me consider something like this. Say one resistor is there and one current source is there. Here there is a voltage source, and here another resistor is there, and here also another resistor is there. So say this is 1 ohm, 1 ampere, 2 ohm, 3 ohm, and say this is 4 volt. So first I'll get the nodes. So we are free to assume any terminal to be ground. So we'll assume this to be ground. And after assuming this to be ground, I'll have to find what are the nodes available. So I can see that this is one node, this is other node. So this is V1 and this is V2. So from directly applying KVL from V1 to V2, we'll get that V1 is equals to V2 plus 4. So from this, I got one equation. The other equation I need to get. So the other equation can be obtained by considering these two nodes as a single node and redrawing the circuit. What I mean to say is, say this is that single node that we have it here, and there are four such branches coming out of it. And this is ground. So this is 1 ohm, this is 1 ampere, this is 2 ohm, this is 3 ohm, 3 ohm. Sorry, I have written volts over there. This is 3. Okay. And this terminal is considered to be as V1 and V2. So we need to use both the V1 and V2 when we are writing the equation. Say the current is flowing outside. So the summation of all these currents will be 0. So from KCL, we got that summation of all these currents will be 0. So while considering these two, I'll consider V1, and while writing the current in this, I'll consider V2. Why? Because these two are connected to V1, these two are connected to V1, and these two are connected to V2. So that's why I have not interchanged any elements, and I have considered the in the same format. So if I consider sigma I like that, I'll get V1 minus 0 by 1 plus 1 ampere. These are this current and this current. And in 2 ohm and 3 ohm, we'll get V2 by 2 plus V2 by 3. And V2 by 3 is equals to 0. So now we got another equation 2. And this node is called supernode, which we got by removing the voltage source. So if you can correlate between these two, here we have Supermesh, the mesh obtained by removing this current source. And here we got the supernode, which is by removing this voltage source. So you can correlate with each like this example as well as this example. So they're just analogous to each other. In that case, it is current and mesh. Here it is a voltage source and nodes. So if you have no more queries in this aspect, then we'll move on to the next topic. So I just wanted to revise this aspect because I have not specifically mentioned the word supernode in my last session. So just for that, I wanted to brush up that aspect again. So I hope it is clear now. If you have any doubts, you may ask at this point, or we can move on to our today's topic. Okay. So our today's topic is the week 2 is a deeper look into the energy storing elements. So which are the energy storing elements that we'll be discussing today? Hello. Anyone? What are the examples of energy storing elements?
Capacitor and inductor.
Inductor and
Inductor.
Inductor and capacitor.
Yes. So we'll be discussing about inductor and capacitor. So before we directly go into the problems, I just wanted to revise the relation between voltage and current in the inductor and capacitor. and how it is different from resistor. Just a few minutes we'll spend here before we go into the problem solving session. So say I am considering resistor, and I am considering inductor, and then I am considering capacitor. So this is R, this is L, and this is C. So whether resistor is a memory element or memoryless element?
Memory-less element.
Okay, and why it is memoryless?
Because it dissipate all the energy.
Okay, that is actually a term used to say about energy storing. Memoryless is a different aspect. We'll come to that. Inductor and capacitor, are they memory or memoryless?
Memory.
Memory element.
Okay. So when we say memory, it means that, say, in the case of resistor, the voltage and current relationship, if you consider V is equals to IR. So let me write it. V is equals to IR. So when I say V is equals to IR, it means the current that is flowing through resistor needs the voltage information at that particular moment, not any voltage information in the past, only at that particular moment. So I of t is only dependent on V of t. So from this I can write I of t is equals to 1 by R into V of t. So it is not dependent on what voltage is across the resistor few seconds before, or some few milliseconds before. It only needs the voltage across that resistor in that particular moment. So when you come to inductor, what is the voltage current relationship in an inductor?
Sir, VL equal to L into di by dt.
Yes, so VL is equals to L into DIL by dt. So I am considering this IL. So again, when we write this equations, one thing we should be very careful is with the polarity. So uh, let me write this polarity. So I am considering in this polarity plus minus VL, and the current is coming like this. So that's why it is plus. So if you reverse this polarity, then this equation will not hold good. It should have another minus sign. So depending upon what inductor current and which terminal you are considering as the positive, that decides the equation. So the inductor current, the current that is entering which terminal, that terminal will be positive in both capacitor as well as inductor. So this is plus VC. So from here, if I want to write the expression for inductor current, what I will be getting? I will be getting IL is equals to 1 by L into integral
1 by L integration of VL dt.
VL dt. So if I want IL to be at a particular time t, IL of t. Say the circuit is running before t equals to 0, or say the circuit has started at t equals to 0. Before t equals to 0, so the circuit is open and it is for infinite time, and we are starting at t equals to 0. So then it will be from 0 to t. So for getting the inductor current at a time t, we need the information of this voltage from the 0 to t. So it needs the information of the inductor voltage in the past. So it needs all the information in the past. So that's why we call it memory, because it has to like in the memory, in the sense, so it is storing all the information of the voltage, and accordingly the inductor current is changing. Whereas in the case of resistor, it is at that instantaneous, so it does not depend what voltage has been applied few moments before. But if I want to know the the resistor current at this moment, I want to know the information of the voltage at this moment only. Similarly, in the case of capacitor, what is the relation between capacitor as
Equal to C into d by dt.
Yes, IC is equals to
C into d by dt.
dVc by dt. So in this case also, if I write VC expression, it will be 1 by C integral 0 to t IC of t dt. So in this case also, say this is again VC of t, as it is changing with time, we are naming it as Vc of t, which is a function of time. So in this case, the same thing is happening. It needs the information from 0 to t. So again, it needs the information of the capacitor current in the past. So it is having some memory. Depending upon that, the present capacitor voltage is decided. So that's why we say this is memoryless and these two are memory elements. So this is one aspect. So say this is point 1. Now we are going to point 2. So whether the current in the resistor can change instantaneously.
No, sir.
Why so?
In here, current depends upon the amount of the magnitude of the voltage.
Okay.
If voltage changes, then why then
Okay, say the
the
voltage
current
is
changes.
changing, then can the current change
Then
instantaneously?
current also changes.
Yes. So
Yes, sir,
here
instantaneously.
there is a
Instantly.
possibility that current can change instantaneously. Like in this moment, current can be 0. In the next moment, the current can be 5 amperes because the voltage is changing.
5 amperes.
Yes.
Linear
Yes,
linear
sir.
relation between voltage and
Yes,
current.
yes. Linear
For
relation
resistors.
and current can change instantaneously. Okay. By the way, were you able to access the YouTube videos and all the lectures that I have uploaded to Google Drive?
Yes, sir. Yes, sir.
Okay. So in the case of inductor, can the current change instantaneously? Like, can there be a step in inductor current?
No, sir.
No,
No, sir.
current,
Okay, why
No
so?
instantaneous change.
it will take time.
Yes. One reason is because of this di by dt. Say if
Stored energy.
yes, if di by dt, say if I have considered inductor current to be a step, something like this. Say this is IL. So at this instant, so di by dt is nothing but the slope of the current, right? So
Correct.
at this instant, slope is infinity or tending to infinity. So which means at that moment, the voltage across the inductor is infinite. So it will blow up. So in practical situation, inductor current cannot be discontinuous. So it should be continuous, and that's why it cannot change instantaneously. So in other way, we have to say inductor current will be continuous. So or we can also say inductor current cannot change instantaneously. So IL cannot change instantaneously. So likewise, what cannot change instantaneously in the case of capacitor?
Voltage, sir. Voltage.
Voltage.
Voltage. And why so?
That depends upon the dv by dt.
Yes. Here in this case, it is dVc by dt. So the capacitor current is dependent on the slope of the capacitor voltage. So the capacitor current will be tending to infinite if you suddenly change the capacitor voltage. So and then again it will blow. So IC cannot be that much high. So VC cannot change instantaneously. Okay, and coming to the third aspect, out of all these three elements, the resistor, capacitor, and inductor, which are energy dissipating and which can store energy?
Resistor is the energy dissipating element, and capacitor inductor store the energy.
Okay, yes. So this is this dissipates energy. So resistor dissipates energy, and these two stores energy. So that's why we call it energy storing elements, the inductor and capacitor. So as we have said, energy storing elements. Okay, so now we have discussed about the inductor capacitor voltage and current relationships and why they are called memory elements and memoryless elements. Before we go into problem solving session, if you have any questions, you may ask.
Sir, can inductor and capacitor dissipate energy?
No, yeah, that is actually a good question. So, actually, someone has asked in the chat, sir, please discuss Supermesh and Supernode. I'll first clarify this whether this can dissipate energy or not, and then I'll get back to Supermesh and Supernode. Okay, so if we come to a practical scenario, say I'm buying an inductor from some shop and I'm using that inductor in my series RLC or RL circuit. So what actually happens is ideally or theoretically when we speak about inductor, we consider only pure inductor and nothing, no other element that is present in the inductor. So our ideal inductor, so let me use a different color. So our ideal inductor will be something like this. Okay. So here there is no dissipation. Now, if we consider a practical inductor, the inductors that we buy in shops or that are connected in the circuits, they have something called series resistance. So with that inductor, you will get slight series resistance. Say I'm buying one microhenry inductor, say 1 microhenry. There could be some few milliohms resistor in that series path, say 2 milliohm. It is very less, but it will be there, and it is inevitable. It will always be there. Maybe the value could be a fraction of milliohm, but it will be there, and we cannot make only pure inductor whatever we are using. People try to manufacture inductors so that this value will become will be as small as possible, and depending upon that, the energy dissipation factor will change. So let us assume we have bought 1 microhenry and there are 2 milliohm resistor in series. So now what happens is not only this inductor has a storing element. So this is our entire product. So if we buy an inductor, so say this is like inductor and it has two terminals. So this is terminal A, this is terminal B. So you have seen different type of inductor, toroidal inductor, wire wound inductor, so different types of inductor. So it is two terminal. So in between these two terminal, it has inductance as well as in series some resistance. So depending upon this value of resistance, how much energy is dissipated in the inductor will be varying. So in this case, say a current I is flowing. So maybe I'll use a different, say current I is flowing. So now power dissipated in this circuit will be I square into R. So 2 million. So it will be 2 I square milliwatt because I have taken the milli outside. So say the current is 1, say current is 1, then the power dissipated will be 2 milliwatt. The power will be the dissipated power is less, but there is some power that is being dissipated. So in the case of only pure inductor, there will not be any dissipation. But in the practical scenario, there will be some series resistance in series with the inductor, which will be causing some power dissipation, maybe low, depending upon the resistor value. Yeah, someone is trying to say something. Okay.
No, sir, not anything.
Okay. So similarly,
Okay, sir.
if I consider inductor or sorry capacitor, this is ideal capacitor. So there is nothing in series, so it will have no dissipation factor, and this is in idealistic sense. But if you buy a capacitor, it will also have some series resistance. So if you want to know the name, this resistance in inductor is called as DCR, DC resistance, and this resistance is called as ESR, equivalent series resistance. Say this is smaller and the capacitor is C. So our capacitor, say whatever capacitor we have bought, something looks like this, and it has two terminals, or maybe an electrolytic capacitor.
Sir, what is the mean of equivalent series resistance?
So equivalent series resistance is between that two terminals of the capacitor. How much is the resistance that is in series? So that is the ESR. So they have denoted it NM. So it is called equivalent series resistance. At this point, you need not know. I'm just giving some information, so you'll be able to understand it better. So they say these two are the terminals of.
Sir, it's an internal resistance of capacitor.
Yes, yes. So when the capacitor is manufactured and when you're buying the capacitor, whatever capacitor you see, say these type, you might have seen these type of shaped capacitors, or maybe these type of shaped capacitors. So you are having only two terminals outside. So those are these two terminals, A and B. But within those two terminals, along with the capacitor, there is some parasitic resistance that is also coming, and it is just part of any practical capacitor. Maybe maybe that resistor could be low. Maybe it is somewhat high, depending upon what capacitor you are buying. So it may be from few milliohm to few ohms. That again depends upon what type of capacitor. There are ceramic capacitor, there are electrolytic capacitor, there are tantalum capacitor. So disc capacitor. There are so many types of capacitor, and this R value could be high for few of the capacitors and could be low for other capacitors. So depending upon their chemical composition and what it consists of, this R value will vary. So I'm considering in general a capacitor, and it also has some series resistance. So this is again practical capacitor. And it will have again dissipation. Say if I want to call it P dissipation. Again, it depends upon IC square into R, whatever. Say the current is IC flowing in this. So depending upon the resistance value, the power dissipated will be depending. Say if it is in milliohm, then it could be few milliwatt, but there will be very light, very less power dissipation. Yeah, but this is how it happens in practical scenario. So overall, when you are talking about an inductor, there is some resistance sitting inside that inductor, like in series, when we talk in equivalent sense. So they are not trying to make that resistance. They are trying to only make the inductor, but whatever wire they are using, etc., will have some finite resistance, and that will be appearing as if it is in series with the inductor. So because of that, we'll observe few parasitic in series. So now just getting out of this domain, and I'm asking like, how will I know how much resistor is there? So there is some meter, as you know, there are multimeter which are used to measure inductor, capacitor, resistor, not inductor, capacitance, resistor, different type of voltage. Similarly, there is something called LCR meter, which is mainly used to measure the inductance, capacitance, and the resistance of any device. So using this instrument, we can get how much series resistance is there, how much series resistance there in capacitor as well as inductor. But this is just for your knowledge, but it will not be part of this course or part of your exam, just to know so that you'll understand in your next year's in E department that there is some resistance which is causing some dissipation. Also, if you want to get the exact value of the parasitics, there is something called LCR meter. Using that, we can get the information. Yeah. I hope this is clear.
Yes, sir, clear.
Okay. So someone has asked one query, so I'm just quickly going back. So Supermesh is a scenario where a current source is being shared between two meshes. Here we have this mesh I1 here, and here we have I2. So this current source is being shared among both these meshes. So in such scenario, if you directly apply mesh analysis, hello, sorry, your voice is breaking. Okay. So you cannot directly apply KVL in this mesh because we do not know the voltage across this source. So one equation we get is if the current is I1 in this mesh and I2 in this, I got one equation directly by this relation that whatever current this current source is carrying. So in order to get another equation, what we do is we remove this current source and whatever mesh we are getting, in that mesh we apply KVL. So this mesh, the mesh that is left over by removing the current source, which is shared between two meshes, that mesh is called Supermesh, where we have removed this source, no source. We have removed that source. And in this remaining circuit, if we see I1 is flowing through 1 ohm and I2 is flowing through 2 ohm. So now we have applied KVL in this mesh, which is this Supermesh, and this will give us the second equation. So now we have two equations, equation 1 as well as equation 2. So by solving these two equations, we'll get the I1 and I2 values. So this is about Supermesh. So the same analogy we can apply to Supernode. In the case of Supermesh, current source is common between two meshes. In the case of Supernode, a voltage source will be sitting in between two nodes, And in this case also, we do not know the current that is flowing in this voltage source. So we cannot directly apply KCL at any node. So in that case, what we do is, similarly, how we got a relation between I1 and I2 directly, we here also will get a relation between V1 and V2 directly because there is a voltage source sitting between these two nodes. So how did we get Supermesh? We have removed the current source and whatever that is left over, that is called Supermesh. So here also Supernode, we'll remove this voltage source and short these two. So now we assume that both V1 and V2 are sitting at the same potential, and this node is called Supernode. So in the case of Supernode, we have to be careful. So now we are applying KCL, and KCL, we have seen 4 branches are there. So when you are applying KCL for this two elements, we have to consider voltage V1 because they are connected to voltage V1 in the original circuit. And these two elements, we have to consider voltage V2 because these two are connected to the voltage V2. So that's why we have got these currents, this say I1, I2, I3, and I5. So V1 minus 0 by 1 is my I1, 1 ampere is my I2, and V2 by 2 is my I3, and V2 by 3 is my I4. So the summation of all this will give 0. So now I have one equation here and one equation here. By solving this, we'll get V1 and V2. So I hope this is clear how to use Supermesh and Supernode.
Yes, sir, clear.
Okay.
But are more than 2 meshes available? We can call
then also we can do the same. So this is for, say, one such current source is there. So if there are two such current sources, then you have to remove this current source and that current source, and you have to apply the KVL. Say then you will be needing, how many equations? Say there is another current source here. Okay, first of all, there is less than a minute. So if this meeting ends, kindly join back into the same meeting, and we'll be continuing our discussion. See, what you are trying to say is, see, there is this current source here, and current source here. See, something like this is there. So I'll consider I1, I2, I3. Okay, so from here I will get equation 1, the relation between I1 and I2. And similarly, I2 and I3, I'll get another relation here, equation 2. Now I'll remove both of them and I'll consider the outer mesh, which is the super mesh, which will. Okay, so say if we have two such sources, then what we are doing is from each of the source, we'll get one equation. So each source will. So say
in Supermesh, if we remove,
sorry.
then in this situation, in Supermesh condition, if you remove that part, then there are two currents in same series line I1 and I2. It is
Yes.
possible.
Yes. So what we actually do is this is just a hypothetical circuit that we are considering to solve this equation. So what here we have done is we have removed this current source. But if I1 is flowing in this element, I2 cannot flow here because they are in series. But what we have done is there is a current source sitting here, but we have removed that and we are applying KVL in the outer mesh. So previous, you have to consider what current is flowing through which element when the current source is connected. So when the current source is connected, here I1 is flowing and here I2 is flowing. So if you apply KCL here, I will get I1 is equals to I2 plus 3, right? So that is giving me this expression. So now I am removing the current source and keeping the circuit as it is. This is not possible actually. Practically, if this is I1, this cannot be I2. This should also be I1. But this is not our actual circuit. Our actual circuit is this, and we are removing the current source and keeping the current same. We are applying the KVL. So this has actually mathematically come. Like if you solve this main circuit, you can get this similar equation. But this is just a trick. So instead of solving that circuit, if you do this, then you will also be and you will also end up getting the same answer. So that is the trick. So the trick is you just have to remove the current source and see which element is carrying what current when the current source is connected in the circuit. Using the same currents, you have to apply KVL. So here also, if you consider this circuit, in this I1 is flowing, in this I2 is flowing, and in this I3 is flowing. So even after removing these current sources, I'll keep the current same, and then I'll apply the KVL to get the third equation. Similarly, if you see in the supernode, this voltage is at V1, this voltage is at V2. But when I'm considering supernode, I'm assuming that V1 and V2 are sitting at the same potential. But one thing I'm making sure is while writing KCL, I have made sure that these two elements has V1 expression and these two elements has V2 expression. Why? Because in my previous circuit, these two elements are connected to node V1 and these two elements are connected to node V2. So I am doing this for my simplicity so that I will get another equation, but I am not changing the fact that these two are connected to V1 and these two are connected to V2. So following the same convention, we are getting another equation so that we can simply solve. This is one way. If you want to go actual way, the actual way is considering a current I here. And if you solve this node, we'll get equations in V1 and I. And if you apply KCL here, you will get equation V2 and I. And this is the third equation. So now we have V1, V2 and I. So we'll have three equations, three unknowns. But instead of making it lengthy, there is this simple trick which we can follow so that we will get two equations directly instead of considering any unknown, extra unknown I. Is that clear?
Yes, sir. Clear.
Okay. So now, yeah, so we have completed, first we have revised whatever that was not covered clearly in the last week, which is this Supermesh and super node. Now, before going into problems, we have discussed some basic introduction about inductor and capacitor, the equations relation, which dissipates energy, and then someone has asked whether inductor can dissipate energy. Yes, in practical scenario, there will be some resistance. Similarly, in the capacitor, there will be some series resistance. But this dissipation will be very, very less because this value of the resistor will be very less depending upon what inductor and what capacitor we have selected. And at times it could be somewhat more also depending upon what capacitor we have selected. Like film capacitor is different, ceramic capacitor is different. So their manufacturing process itself is different. Their material could be different. So as material is different, their characteristics will also be different, and accordingly the resistance value could also differ from different capacitor as well as different inductors. And these are actually provided in data sheet also. So for in the case of inductor, this information is also provided in data sheet. So if we go through the data sheet, so data sheet is nothing but some sheet of information regarding any product. It could be inductor, it could be any IC, any op-amp. So they'll provide the datasheet. So going through that datasheet, we'll understand everything about that particular element. So they'll be doing some tests on that inductor, and they'll give all that necessary information in that particular datasheet. Okay, so before we go into problems, I wanted to make sure if anyone have any queries, then we can discuss, else we can go to problem solving session.
No, sir, no, sir.
Okay.
No query.
Okay. So yeah, let me open one of the problem solving set. So we'll go to this assignment 2. Yeah, actually assignments I cannot share because these are only given to TA. So I can discuss these assignments, but I'm not allowed to share this PDF. So for that reason, I'll not be able to share this.
Okay, sir.
Okay. I think this is creating some issue. Let me close this. Okay, so we have the assignment here. Let me open my writing pad. Many tabs are open, so that is why my computer is hanging a bit. Okay, we have the we'll might not be able to solve all the questions, but I'll select few problems, so which should be sufficient to have a better understanding of all these aspects. So from there we'll be able to get some overall understanding. Yeah. So okay. Let me open this. So first question, we'll be taking this question where they have given voltage across the capacitor, 4 waveforms, and from the inductor current, we need to get the voltage waveform. Okay, so let us go back to our writing notes, and yeah, we are considering problem solving. So these are problem solving session. Okay, so I'll just take a screenshot of this. And we'll copy it in this. Okay, so this is the question that we have copied from there. Yeah, and it says find the voltage across the 5 microfarad capacitor if the current is associated as shown in this figure. So this is this capacitor I of capacitor current I of t. So this is question 1. So how can we proceed with this? So how to solve such type of questions?
I is equal to C dVd by dt.
Yes. So whatever we know regarding the capacitor, we'll be using that only. So I of t is equals to C into d V of t by dt. Right. So I consider some basic. There are 2 type of ways. One way is to directly integrate the current and get the necessary information, like what is the waveform of the V of t, because if I know the waveform I of t, I can directly get V of t by integrating it. But instead of doing it mathematically, I can also do using some trick. So one thing I know from this thing is say my I of t is 0. What that means? If my I of t is 0, what that means? What will be the V of t?
Initially, the capacitor is
Sorry.
open circuit.
Okay, that is okay. But say from this expression, if I
Constant.
say yes, V of t is constant. So if voltage of the capacitor is constant, it means the current that is entering the capacitor is 0. So anytime I see I of t is 0, which means the voltage of the capacitor is constant. Or say I of t is some value k. I of t is some constant value k and it is fixed. Then can I say anything about V of t?
Linearly varying.
Yes, V of t is linearly varying. And yeah, that is actually right word. We do not know whether it is increasing or decreasing. It will increase if k is positive. It will decrease if k is negative. So V of t have two such conditions: linearly increasing or linearly decreasing. So first one is linearly increasing. It will happen when k is greater than 0. The other one is linearly decreasing if k is less than 0, because if the current is negative, then it will discharge. If the current is positive, then it will get charged. So using the same thing, this information, I'll get to draw the voltage waveform. So one thing that we need to keep in mind is they have said the capacitor is initially uncharged. So it means VC of 0 minus is equals to 0. So in the beginning, the capacitor is discharged. So until this moment, the capacitor voltage is 0. So let me draw. Okay, so this I have drawn. And from whatever information I got that at the beginning, the capacitor voltage is 0. So until this point, my capacitor voltage is 0. So this is, sorry. So this is my VC of t. And this is my time t. So from whatever information I got, I came to know the fact that in the beginning it is 0. So now my inductor current is a positive constant. So what that means? What happens to the capacitor voltage? Hello. If
Sir,
my
please,
Hello.
uh,
sir, please,
yes, so okay, let me
one
repeat.
second.
Yeah, I'm saying until this point it is 0 because they have said that capacitor is initially uncharged. Now capacitor current is some positive constant value. So if it is some positive constant value, what will happen to the
Sir, it is
capacitor voltage?
constant and then linearly increasing and then constant.
Yes. So in this region from 0 to 2 millisecond, I of t is constant. And not only that, I of t is constant. And not only that, the constant value is positive. So my V of t will be linearly increasing till 2 millisecond. Okay. So I will draw again this. See, it is linearly increasing till 2 millisecond. So let me get, so what, until what value it will increase, that will come back. But we'll assume that it has linearly increased to some value. And this is 2 millisecond. So from 0 millisecond to 2 millisecond, it has constantly increased, linearly increased. And after that, inductor current has become 0 again. So it means the capacitor voltage is constant. So whatever value it has reached in this 2 millisecond, it will be constant. So one thing we have to keep in mind is we have understood that capacitor voltage is continuous. So that's why it remains constant with this same value. Okay, and for the other type. So this is the waveform of the capacitor voltage. Now the big question is, what is the value of this peak? So how will I know? I will be using this equation. I of t is equals to C into dV of t by dt. So that equation says I of t is equals to C into dV of t by dt. So dV of t by dt is the slope of this curve, right? So I will find the slope of this curve, dV of t by dt, which is nothing but my I of t by C, right? What is my I of t and what is my C? Whatever is given in the question. 20 milliampere and 5 microfarad, right? Hello.
Sir, sir.
Yes, 20 milliampere and 5 microfarad. So 20 milliampere and 5 microfarad. So it will be 4 into 10 to the power 3. So the slope at which the voltage is increasing is 4 into 10 to the power 3. So I know the slope of this. Say this is K. I know the slope of this, which is K. So using y equals to mx or y equal to kx in this, I need to know the value of y at x is equal to 2 milliseconds, right? So I'll substitute the values. Y is what? My Vc. K is what? The slope, 4 into 10 to the power 3. And x is what? My time period, 2 milli, 10 to the power minus 3. So from this, I will get Vc is equal to 8 volts. So my Vc has increased till 8 volt in this duration. And after that, the capacitor current has become 0. So it will stay at that voltage. So this voltage is 8 volt. So if you have any questions till this point, you may ask, or if you want me to repeat this again,
No, sir.
I'll
No.
repeat. Okay. If
Sir,
anyone has,
please repeat this again.
okay. So you
Sir,
have
from starting.
okay from starting. Okay. So they have given a voltage source V of t or the voltage across the capacitor, and they have given I of t waveform. So from this I of t waveform, they are asking how does the capacitor voltage will look like. So before going into the question, I have discussed few aspects here. I have told, or we know, the relation between the capacitor current as well as capacitor voltage is this. So from this, we came to the conclusion that if I of t is 0, which means this is 0, so the slope is constant. The slope is 0, which means V of t is constant. So if V of t is constant for a time, then the slope is 0. So I of t is 0. And if I of t is some constant value
Yes,
k,
sir.
then voltage will be the integral of that constant, which means some linearly increasing or decreasing depending upon the k. So if k is 0, then it is constant. If k is greater than 0, it is linearly increasing. If k is less than 0, linearly decreasing. So now if we come back
Yes,
to
sir.
this point, initially capacitor current is 0. So that says our voltage will be constant. But what value of constant? For that, they have given that initially capacitor is discharged or uncharged. So
On card.
initially capacitor voltage is 0. So from that, we got to this conclusion that initially it will be sitting at 0 volt. So after this 0 millisecond, my the capacitor current is a constant positive value. So if it is a constant positive value, then it means it is linearly increasing. So I have considered voltage linearly increasing until 2 milliseconds. So until 2 milliseconds, it is linearly increasing. After 2 milliseconds, then it again becomes 0. So if it is 0, voltage will be constant. As my capacitor voltage cannot be discontinuous, whatever voltage that it has been charged to till 2 millisecond, it will stay at that voltage, which is unknown until this point. So first I have drawn the curve. Now I need to find what is this voltage. So again I came back to the capacitor current as well as capacitor voltage expression. So I of t is equals to C dV of t by dt. So in this region, only in this region. So if I'm considering only in this region, I of t they have given to be 20 milliampere. And C they have given 5 microfarad. So I got the slope. So I calculated the slope with which the capacitor voltage is increasing. So if I know the slope using y equal to mx, some mathematics, I want to know this voltage. So if I know the slope, I know it is starting from 0, 0. So if I want to find this voltage, I'll directly substitute x is equals to 2 millisecond and the slope is 4 into 10 to the power 3. So my VC is 8 volt. So this is my final graph. So let us check if it is correct or wrong. So out of these four, which is the correct answer? These four graphs?
B option.
B, option B. So
Option
we'll
B.
check. Yes, so option B is the correct answer. So yeah, I hope you are able to understand this question, how to get different waveforms when they have given the current or voltage information.
Yes.
Okay. So we'll move on to some other question. Yeah, we can also solve similarly. We can solve this inductor question so that we'll get a overall understanding of both capacitor as well as inductor. So I'm considering a similar inductor question. So I'm considering this inductor question to be problem 2 and we'll solve. Okay, so this is problem 2. In problem 2, they are saying find the waveform of the current in a 3 Henry inductor. So they have given L equal to 3 Henry. As shown in the figure, determine the inductor voltage waveform. So they have given I, now we have to find V. So this is just vice versa. Previously, they're asking, they're giving this information and we need to integrate it. Now they have given the current information. So what is the relation of inductor voltage and inductor current?
EL equal to L into di by dt.
Oh, yes, so it is L into di by dt, di of t by dt. So now we have to differentiate it. Okay, let us differentiate it. So before that, let me draw the plot. So this is my y-axis as well as my x-axis. Now I'll name this v of t and this is time period t. So we'll do division by division. So from minus infinity to minus 1, my I is 0. So what will be my voltage? Hello. My I is
Current
0.
will be 0.
So voltage will also be 0. Yeah, you are right. So let me use a different color. So from here to here, it will be 0. From minus 1 to 0, my inductor is linearly increasing. So if I want to find V of t, I need to know the slope of that and I have to know the inductor value. So in this region, say I am marking this region 1 and I am marking this region 2 and I am marking this region 3. So in the region 1, so in region 1, we need to find the voltage. As the current is linearly increasing, voltage will be what? So the current is linearly increasing. So whether the voltage will be linearly increasing, constant, or quadratically increasing, decreasing, what?
Linearly increasing.
A constant value.
Yes, constant value. Because if you plug in this I of t here, if I of t is linearly increasing, the slope of I of t is constant. So V of t will also be constant. So V of t is inductor value 3 into the slope of I of t. What is the slope of I of t in this region?
1.
1. So my V will be at 3 volt and it will be constant throughout this region. So I'll come back here and it is, so this is 3. And it has gone from 0 volt to 3 volt. So this is 0 volt and this is 3 volt. So now we are at the end of region 1. Now we'll go back to region 2. So in region 2, current is constant. So what will happen to the voltage?
0.
0. Because if the current is constant, the slope of the current is 0. So my V of t will be 0. So during this region, when the time is from 0 to 2, my inductor voltage is 0. So now I'll come back to again 0. So first I'll come back to 0 and then from 0 to 2 it is staying at 0. So this is again, sorry, 0 volt. Now we'll go to 2 to 3, which is region 3. So it is pink color. So again, inductor current is linearly decreasing. So what happens to the voltage of the inductor?
Constant but negative, magnitude of -3.
Yes. So the inductor is a line with a negative slope. So di by dt is the slope. So as the slope is negative, this will also be negative. So voltage will be a negative value and the magnitude is V of t is equals to L into that slope. So L is, they have given 3. And what is the slope? Can you tell me? Hello, what is the slope?
-3.
Minus 1. Slope is -1, voltage is -3. And after 3, again, inductor current is 0. So what will happen to the voltage after 3?
Again 0.
Again 0, because if the current is constant, it will become 0. So during 2 to 3, it is at -3. And after that, it is again 0. So if I write, this is minus 3 volt. So this is -3 volt. And then this is 0 volt. So did you understand? Or let me just revise this again. They have given inductor current in this case, and they have asked us the V of t waveform. So they have given the inductor value as 3 Henry. Now we have divided it into subparts from -infinity to -1. It is given that inductor current is 0. So if inductor current is 0, the derivative is 0, voltage is 0. So from -infinity to -1, it is 0 volt. In this region 1, where the inductor is linearly increasing, the slope will be a positive constant. So V of t will be a positive constant multiplied by L. So this positive constant or the slope of the I of t is 1 multiplied by inductor value 3. So it is 3 volt. From -1 to 0, it will be 3 volt. 3 volt. At 0 volt, I of t is a positive constant. So it is a constant, derivative of it is a 0. So V of t will be again becoming 0. In the case of region 3, inductor current is falling with a constant negative slope. So the derivative of it is a negative constant, and that negative constant is the slope of this. Slope of this is -1 multiplied by inductor value. Inductance is -3 volts. So V of t is -3 from 2 to 3. So in this 2 to 3 region, it is -3. After that, inductor voltage has become, inductor current has become again 0. So the derivative of it is 0. So the voltage is also at 0. So is this clear? This question, how we have solved, how we got this?
Yes, sir.
Yes, sir.
Okay. So we'll go back to this. So what is the correct waveform? A or B or C or D?
B.
B
B.
option.
B.
Sir.
B.
B option correct.
No, sir. C option.
C option.
Yes, yes. See, if you see, you have to be careful. Both
C
are having the
option.
same option, but this is having 3 volt and this is having 1 volt. So sometimes these will be tricky. When you are choosing the option, you should be careful. See, even after doing all the calculation and getting the correct waveform, we are confused and they have given this same waveform with different values. So we have to be very careful when we are selecting the options. Yeah. So this is another way problem. So in the first problem, we got to know how to get the voltage current waveform correlation in the capacitor, and then we have gone to the inductor. So yeah, let me check which other thing is good, is dissipated. Yeah, this is another good question. We can solve this question. So let me just take a screenshot of this question. We'll come back here. We'll go to new page. So we are in problem 3. This is problem 3. So the question is, they have connected a voltage, or maybe you just go through the question and think about the solution. So I'll give you a few minutes time, then we'll discuss. So just go through the question and let me know how to solve. So have you gone through the question? Okay, can anyone tell me what needs to be calculated in this question? Okay. So they have given a circuit where a voltage is connected in series with the resistor and it is connected in series with the capacitor. So initially the switch is open. So the capacitor voltage is 0. The current in the
वो
circuit is
100 ohm
0.
resistor में कितना?
Okay.
Yes, sir.
Yeah. So now they are asking, eventually the capacitor will be charged to +5 -5 volt. So now they are asking during during this time, how much dissipation, how much energy the 100 ohm resistor is dissipating. So first we'll see from the point of view what needs to be done. So they are asking energy. So we know that energy is integral of power into time, right? PDT. And power dissipated in the resistor is I square R dt. So I know the resistor value. I need to know the current as a function of time. So I need to know what is my I of t. So I have to solve for I of t. So what is my I of t? Then if I substitute it here, then I'll get to know what is the energy dissipated. So 5 volt is connected in series with resistor, is connected in series with the capacitor. So if I write KVL, can someone tell me what will be the KVL equation?
Sum of all voltages is equal
Yes.
to 0.
So 5 volt plus what is the voltage?
Sir, minus
No, I'm going from here. Yes.
5
Plus
plus
or
IFT into
minus?
100
Plus or minus?
plus minus
Minus. So minus
minus 100 into IFT minus VCT.
Yes. So I'm considering that as V of t is equals to 0. Now I know that I of t and V of t are related like this. My I of t is equals to C into dVt by dt. So I will substitute that here. And the capacitor is given to be 5 milli or 10 millifarad. So if I substitute that, what I'll be getting? I'll get 5 minus 100 into 10 milli is what? 1, right? Or 10. How much? 1, right? How much is 100 into 10 milli? So C is 10 milli, right? C is equal to 10 millifarad. So if I substitute here, I'll get dV by dt, right? Got it?
Yes, sir.
Okay. Now we need to solve this differential equation. So I'll bring dV of t and dt on one side and 5 on the other side. So I think you are taught in your mathematics course how to solve this differential equation, right? So we'll multiply by e power t. Do you know how to solve this equation, differential equation? Hello.
Yes.
Yes, sir.
Okay, so we are multiplying
Both
by
side equal.
e power t. Okay. Then we'll get dv of t by dt. And I hope everyone is solving. Don't just listen to whatever I'm saying. You also do calculation. Then only you'll know how to solve. You might be doing mistakes, so you'll know where you are doing mistake, and you can rectify in the exam. So the LHS side, I can write as d by dt of v of t into e to the power t. And the RHS is 5 into e to the power t. There is less than a minute and this meeting will end. After that, you kindly join back. Then we'll continue our discussion and solve this problem. So until this point, is it clear?
Yes, sir.
Yes, sir.
Okay.
10 millifarad.
Yes. So now I will do d of v of t into e to the power t is equal to 5 e to the power t dt. Now I will put back the integral sign. Integral. I will do from 0 to t, and I know at t equals to 0, my voltage is 0 because they have told. And at t, my voltage is v of t. Is it clear till this point? If this meeting can kindly join back, then we'll continue our discussion.
Yes, sir. Clear.
Okay. So now the integral of this will be v of t into e to the power t minus. So I'm integrating this differential term, this d into v of t into e to the power t, which is equals to 0 to t 5 et. So on the right hand side, I will get 5 into e to the power t from the limits 0 to t. So if I substitute that, I'll get 5 into e to the power t minus 1. Right. So if I take this back, e to the power t onto the RHS side, or if I multiply by e to the power minus t on both sides, then I'll be getting my v of t is equal to 5 into 1 minus e to the power minus t. Right? Is it clear? Hello. Hello.
Yes, sir.
Okay. So I got the voltage of the capacitor as a function of time, but I need current as a function of time. So what is the relation between current as well as voltage? I know that I of t. Just wait a moment. It is finding. So what will be the relation? Can anyone tell me? What will be the how to find the current as a function of time from the voltage? Hello.
I of t equal to C into dv of t by dt.
Yes. So can you calculate? In the meantime, I'll just resolve this. My general app is done. So you just calculate and tell me what will be the expression. Let me just open it again.
Sir, please explain that the question once again.
Which step?
This question.
From the beginning or which part?
Yes, yes.
Okay. So
Initial step.
last step. All the steps.
Initial step.
Okay, okay. So they are asking how much energy is dissipated through this 100 ohm resistor during the charging of the capacitor. So I know that energy is integral of power into dt. So power in a resistor is nothing but I square r dt. So what I'm trying to calculate is I want to get I of t as a function of t. So for getting that, I wrote the differential equation or the KVL of this expression 5 minus 100 into I of t minus V of t, where V of t is the capacitor voltage, is equals to 0. And we know that I of t is equals to C dV by dt. After substituting that, I got this equation 5 is equal to dv of t by dt plus v of t. Now I am multiplying it by e to the power t, so that I got this expression. Now I have integrated it from 0 to v of t and 0 to t on RHS side. And after getting that, I got the expression of v of t as 5 into 1 minus e to the power minus t. Now I have asked what will be my I of t. My I of t will be C into dVt by dt. So C is 10 milli. So 10 milli into 5 into e to the power minus t. So it will be 50 into e to the power minus t milliampere, right? Do you agree? My I of t. 50 into e to the power minus t milliampere.
Yes,
Hello?
sir. We
Yeah.
agree.
Now I want to calculate the energy. So the energy is given by integral of power. It is again causing issue. You in the meantime, you just calculate what will be the current, the energy, which is integral p dt. So integral p dt is what? Hello. I square r into dt, right?
0.05 with 1.
Yes.
I
So
square r into 2.
can you quickly calculate it? Just let me open it. Okay, so let me also write it. The energy E is equal to power of dt. Power is I square r. So I'll get I square as 2500 into e to the power minus 2t into R is 100, right? Right? Into
Yes,
dt
sir.
into 10 to the power minus 6 because it is milliampere. Now if I multiply it, I will get 25 into e to the power minus 2t dt into 10 to the power minus 2. Now from what time to what time will I integrate? Anyone? From what time to what time I should integrate?
0 to t.
0 to t, or they are asking the energy dissipated until the capacitor is fully charged to 5 volts. So when will the capacitor charge to 5 volt?
Infinite.
Infinite time. So we need to integrate it from 0 to infinite. So from 0 to infinite. So if I do that, I will get energy is equal to 25 into 10 to the power minus 2 by minus 2 into e to the power minus 2 from 0 to infinite. If you substitute these limits, you will get 25 by 2 into 10 to the power minus 2 minus is there into 0 minus 1. So we will get energy is equal to minus 12.5 into 10 to the power minus 2 into minus 1. So I can write into 10 to the power 3 millijoules. So this is energy, right? So I'll be writing this in 10 to the power 3 millijoules. So if I do that, I will get energy is equals to 125 millijoules. So did you understand this last part, the calculation? So I have integrated the I square R, or I have integrated the I square R dt over a time period from 0 to infinite. Why? Why did I do that? I did it because they have said find the energy dissipated in the resistor until in the time the capacitor will reach 5 volts. So when will the capacitor reach 5 volt? The capacitor will reach 5 volt at infinite. So we have to calculate the energy dissipated in the resistor during this infinite time, and the circuit has started at t equals to 0 and it ended at infinite. So what I have done, I have integrated from 0 to infinite, and they have asked the answer in millijoules. So if you see here, they have asked the answer in millijoules. So I have calculated in millijoules. So I went back here, I got my answer 125 millijoules. Are you also getting the same answer?
No, sir, I have getting
Yes, sir.
Okay. You kindly check if you have made any mistake. It should be around 125. So now let us check with the answer. So the answer is a range answer, and it is
Okay,
from
sir.
120 to 130. So our answer is matching, and it is 125 millijoules. So if anyone has any doubts before we further move on to other question, you may ask. So this is some interesting question where we are finding the energy or a infinite time period. Is this question clear? Hello.
Yes, sir, clear.
Yes,
Okay,
sir.
okay. So we'll
Yes, sir,
move on to
clear.
some another interesting question. So let me check. This is okay. Okay. So we'll start with this question. The question number 1. So this is also another interesting question. So our will be problem 4, right? Yeah, problem 4. Okay, so this is problem 4. So how to solve this? So they have given the current through an initially uncharged 50 millifarad capacitor is given above. Find the voltage at 1 second. So they're asking the voltage at this instant, which is 1 second. So how to proceed? Can anyone say? Hello.
Okay.
Sir,
Any
by
idea?
integrating all the time
Yes,
limits
yes,
there.
yeah, very good. So we know that I of t is equal to I of t is equals to C into dV of t by dt. Okay. So if I come back here, I'll get V of t is equals to 1 by C into integral I of t dt. So if I want voltage at a time t, I will integrate it from 0 to time t. So if I want voltage at 1 second, so if I want voltage at 1 second, I will do 1 by C into integral 0 to 1 second I of t dt. I of t dt is nothing but area under the curve I of t, right? So we need the area under this curve multiplied by 1 by C. So now I'll divide this into multiple regions. So if I divide this into multiple regions, I need to find the area of this. So this is one. This is the other one. And this is another one. And this is the other one. So can you tell me what will be the areas of this? So what is the area of this?
0.4
0.2
into 5.
0.2 into
Area
5. So how
1.
much will be the value? Area 1 will be
1.
1, right? And what will be this value? Area 2?
2.
And
Mm,
what will be this
10
value?
into 0.4.
Not 0.4, it will be 0.4 minus 0.2 because it is the difference, right? Got it? Which is, this is 10 into 0.4 minus 0.2. And what will be my A3? A3 will
1.
be again 1.
5
And
into
A4?
0.2. 1.
Yes, and A4?
10 into 0.2.
2.
2.
Only 2.
Yeah, because it is not 0.8, it is the area. So breadth is 0.8 minus 0.6 and height is 10. So 10 into 0.8 minus 0.6. So now the total area will be 1 plus 2 plus 1 plus 2. So if I have to find this, I have to do 1 by C. C is 50 milli. So 50 10 to the power 3 into 1 plus 2 plus 1 plus 2. So my numerator will be 20 into, this is what? 4 plus 6. Right? Is my calculations correct? Just check.
Yes, sir. Yes. It's
Okay.
120 amps.
So my V at t is equals to 1 second is 120 volt. So I got it by integrating the current, or which is also called as the area under the curve I of t. So that is what I have done. So 1, 2, yeah, someone also mentioned in the chat. Yeah, we are also getting the same thing. So let me just quickly revise or just re-explain what we have done in this problem. So in this problem, they have given the current as a function of time and they're asking the voltage at some particular time t. And if you see this area, there is no area in this region. So the area is 0. So that's why no need to add any value. So it is coming to be 1 by C into area under curve. So area under curve is nothing but the summation of all these 4 areas, which is 1, 2, 1, 2. So this is 1 plus 2, 3, 1 plus 2, 3, 3 plus 3, 6. So the total area is 6 into 1 by C. The answer is coming to be 120 volt. So we'll see what is the answer. So it is in the range 114 to 126. So our answer 120 is correct. So there again, there is a range. So depending upon the range, how much it is coming, we'll get that value. So now, I hope it is clear till this point, right?
Yes, sir.
Okay. So now we'll solve one interesting question. Yeah, this question might seem big, but it is simple question. So we'll solve this.
Sir, for this kind of question,
Yes.
we have to enter integer value or decimal value.
So sometimes if they have any decimal value, they will say that you need to enter decimal up to 2 decimal points or 1 decimal point. If they have not said anything, just write integer value. Say, I'll take some example like in this case. So it is anyway 0. So we'll move on to some other all these answers. So in this case, they have said calculate the power in millivolt dissipated in this, and they have not said that whether it should be decimal or not. So what they do is they are considering 1 decimal in the answer, but it does not mean that you should also consider. So the answer could be somewhere 64, 65, something. And if they have not mentioned anything about the decimal, then you have to directly put 64 or 65, something like that. In sometimes they consider, they'll tell, write the answer up to 2 decimal. Then you have to round it off and write up to 2 decimal. Till now, we have not come across such question, or you just have to go through the instructions. If in the instructions they say that write the decimal point up to 1 point, then you have to write up to 1 point. So you kindly go through all the instruction. Either they will be mentioning the question or they will be mentioning at the top. So if they say 1 decimal, you have to write till 1 decimal. If you have written 2 decimal, then as this is automated correction, and whatever answer they have provided to that automated the solver, then according to that it will correct. So even if your answer is correct, if you write more decimals, it may consider it as a wrong answer. So if they have said, say in this question, as we will be solving, we'll get some value. According to that, we'll see what is that value. Here also we'll see whether we are getting any integer value or decimal value. So here they have not mentioned any such decimal value. So we will see what value we are getting, whether we are getting integer value or not. So in this question, they are asking calculate the voltage Vx, assuming the circuit is running for very long time. So as you see from the circuit, it may seem like it's a tough problem, but actually it is not. The big circuit is just to like put some pressure on you, but if you go through whatever knowledge we have acquired in this week, it will be very simple and
Sir, for this kind of
straightforward.
question for a very long time,
Yes.
we have to short circuit that inductor and capacitor open circuit, no?
Yes, yes, you are very right. So this is our problem 5. So when the circuit is running for a very long time, then we know that inductor is shorted and capacitor is open. So this will be
So
shorted.
it's a steady state condition.
Yes, yes. So in the question it is said calculate the voltage Vx, assuming the circuit is running for a very long time. So when they say very long time, it means that the circuit has reached its steady state and all the inductors are shorted and capacitors are open. So in this case, this is shorted, and this is open, and this is shorted, and this is open. So now I will try to redraw this circuit again. So I have a resistor here, and this entire thing I can remove because capacitor is open, and then this is open, this is shorted, so I'll have shorted, uh, and then the voltage source here, and then another voltage source here, and then a current source here, and then another resistor here, and then another resistor here. So the resistor value are 20 ohm, 50 ohm, 15 ohm, 20 ohm, 15 ohm, and 15 ohm. And this is the final circuit in the steady state. So now it is behaving like this. So this is 5 volt. This is x, y plus minus v, x, y. So now we have to solve for this problem. So I'll assume that say for the time being, okay, let me say this first. So how to approach this? So this is what, supernode or supermesh or what type of circuit?
Supermesh.
Supermesh. So as this part is not there, I'm currently removing it as no current is flowing, and even if it remove, there will not be any change. So I will do I1 here and I2 here. Okay, so what I'll be getting, this is again 5 amperes. So I need two equations, two unknowns. So this is my I1 and this is my I2. Okay, so one equation I'll be getting is I1 minus I2 is 5 amperes. Right? Hello.
Yes, sir.
Yeah. The other is by applying
Yes, sir. Yes, sir.
Supermesh. So in the Supermesh, what will be the equation that I'll be getting? 5 outer mesh. So I'm
Minus
considering
20 I1.
Plot 5 minus 20 I1
Minus 15.
minus 30 I2. So series है 30 I2
is equal to 0, right? So we have equation 1
is equal to
and
0. Yes.
equation 2. If you have calculator, can you quickly tell me what are I1 and I2 values? I have also done, we can cross check. Can you tell me what are I1 and I2 values? As I'm not having my mobile phone right now, you just tell me what are I1 and I2. And yeah, everyone should be doing and all the answers should match. Just either you can do it by hand calculation, or if you have calculator, you can also do it by calculator.
खाता
Anyone? What is I1? What is I2?
Sir, I2 is 2.1.
Okay. And I1?
7.1.
2.1 and 7.1. Is it matching? Because it is not matching with my answers.
I2 is 19 amperes.
Or some other value.
0.1 ampere I1.
Okay.
And I2 is also 0.1.
If it is 0.1, I1 minus I2 should be 0, right?
No, sir.
Yeah. You have to be very careful with the calculations, because these are the skeleton of any problem. So you have to be careful. So I1 is nothing but I2 plus 5, right? And the second equation is 5 is equal to 20 I1.
Sir, 1.9. I2
Which one?
equal to 1.9.
Okay. Or plus or minus?
Minus 1.9.
3.1 is I1. I1 3.1 positive ampere.
So I2 is minus 1.9, right? And I1 is 3.1. Right?
Yes, sir.
Yes. So now I got I1 and I2. So now I'll go to the question and I'll see what they are asking. So the circuit is solved. So I have I1 and I2. So now whatever question they'll ask me, I'll be able to do. So they're asking what is the Vx. So they're asking Vx, right? So this is my plus minus Vx. So this is plus, this is minus. So I'll consider this to be ground. So what is the value of my Vx? Is it 15 I2 or minus 15 I2? This is ground. Remember, this is at higher potential. (15I2) or minus 15I2?
Minus 15 I2.
30.
Plus or minus? See, current is
Minus.
flowing. Current is
30,
flowing from
30
this terminal to ground. So this terminal is always at higher potential. So it will be 15I2. Now whether I2 is positive or negative, that is a different issue. But according to my convention, I2 is flowing from this terminal, say X terminal, to this ground terminal. So according to my convention, X terminal is at a higher potential. So my Vx is 15I2 and Vx is 15 into minus 1.9. So what is the answer, Vx?
Minus 28.5.
28.5.
Sorry, it should be 15 or 30.
28.5.
30. It should
So
be 15 or 30. 30 I2. 30 I2.
So 30 I2 will be what
15.
voltage? So they are asking Vx. So you have to be careful. Vx is across 15 ohms. So it is not 30, only 15.
Okay. Okay.
Okay. So
Yes.
how much you are getting
Yes.
Vx, everyone? Minus 28.
28 minus 28.5.
Minus 28.5
0.5.
volt. So this is my final Vx. So I'll go back and see. So they're asking Vx with proper sign. So again, minus sign should be there. So minus 28.5. So as you got minus 28.5, you can put minus 28.5 and it is single decimal. Or you can also put minus 28, both will be correct, but you can be accurate and put minus 28.5. If you put 28.5, you will not get any marks. So kindly be careful with that. Now they are asking Vxy. So they are asking this voltage Vxy. Okay. So we'll go back here. So there is this extra circuit here, Vxy. What will be the current flowing in this path?
I1.
In this path? Zero, right? Because there is no current flowing, there is no closed path. This is open. So say this is node A, VA. So what I mean to say is my VY will be zero, right? Why? Because the current flowing through this path is zero. So my VXY is nothing but VA. Do you agree?
Yes.
And what is my VA? From here?
Grade 5 minus 20 I1.
Sorry. 5 minus?
5 minus 20 into I1.
Yes. This is one way.
20 into I1.
Yes. Or it can also be 30 I2, right? Because this terminal, if I go from this path, it will be 30 I2. If I go from this path, it is 5 minus 20 I1. Because from this expression also, I will get 5 minus 20 I1 is 30 I2. So both should be giving me the same value. So what is 30 into I2? Minus 57. How much?
Yes, sir. Minus 57 volt.
So my VA is equal to minus 57 volt, or Vxy is equals to minus 57 volt. So yeah, so this is one question where you need not solve any of the L and C things. You just have to know that when the circuit reaches steady state, inductor will be shorted, capacitor will be open. After doing this, I got this circuit, and then as this branch does not have any significance or any effect on the overall circuit because it is anyway open, I have removed that and I have calculated I1 and I2. Now this is a problem of Supermesh. We have realized that this is a problem of Supermesh. Then whatever we have discussed today, we have applied that and we have solved that equation. We got I1, we got I2, and from I1, I2, we were able to solve whatever it is asked in the question. So whatever voltage we are getting, it is minus 57. Let us go back and see. So minus 57 is falling in this range. So our whatever we have done is correct. So if you have any questions, you may ask, or I'll just revise what I have discussed today and we'll end this session. If you have any questions, then we can discuss, else yeah, we'll go to summary. Okay.
No, sir,
So,
no.
okay, as a summary, in the beginning, I have discussed Supermesh and Supernode because I was I have not covered this in detail last week, so I wanted to cover it again. So I have covered Supermesh as well as Supernode. And we have considered two problems, and I have told you how to get the equations and what logic we need to apply to get the third equation. Then we have started this week's topic, a deep overlook into the energy storing elements, which are inductor and capacitor. Then we have discussed about their voltage current relationships and how these are called, why these are called memory elements, and what can change instantaneously, what cannot change instantaneously, which element stores energy, which dissipates energy. Then from practical scenario, we have discussed there will be some series resistance in series with inductor or as well as capacitor, and these can be measured using LCR method. And then we have solved few problems. In the problem 1, they have given inductor capacitor current, and they have asked us to draw the capacitor voltage. We have drawn, and in the second problem, they have given us inductor current, and they have asked us to draw the inductor voltage. And again, we have drawn the inductor voltage waveform as a function of time. And in the third problem, they have given one question, and this is some tricky question or somewhat lengthy question. So they have said initially it is open, and when they have closed it, as the circuit is on till infinite time, capacitor will be charged till 5 volt at infinite time. They are asking what is the total energy dissipated. So energy dissipated is integral of power into dt, where power is I square R. We know with IR and we do not know I of t. So for calculating I of t, we have applied KVL and substituted the capacitor current voltage relationship in this, and we have solved for V of t. After getting V of t, we know that I of t is C dV by dt. Then I got I of t, then I have integrated in 0 to infinite because capacitor voltage will reach 5 volt at infinite time. Then I got the energy dissipated. In the other question, they have given capacitor current and they have asked the voltage at this instant. We know that this capacitor voltage is 1 by C times area under I of t current. So we have calculated the area and we got the voltage at that time period t equal to 1 second. And in the last question, they have given some complex circuitry and they have said that this has reached steady state. So this circuit has reached steady state. So we know that at steady state, inductor will be short circuited, capacitor will be open circuited. Applying that, we have simplified the circuit, and after simplifying the circuit, we realized this. We realized that it is a super mesh problem, and whatever we have discussed today at the beginning, we have applied it and calculated I1, I2, and then we have seen what questions they were asking, and we have found out the voltages. So with this being said, we can end this session if you have no more doubts. But I just want to ask, you are going through the lecture videos and you are able to follow, right? Whatever I have uploaded in the YouTube, you are able to access that as well as the notes that I have uploaded to Drive, and you are going through them, right?
Yes, sir.
Okay. Okay, if you have any queries, you can ask, else we can end this session.
Question
This slide
says how much power is delivered by voltage or current source. What we should do?
Okay, that is a good question. So in this scenario, if someone asks what is the voltage, what is the power delivered by this source, then power delivered by any source is equal to the voltage into current. So how much current this is supplying? I1, right? So it is 5 into I1. So that is the power that is delivered by this source. Now, one thing you have to keep in mind, and which is very crucial. I1 direction, how I1 is flowing. If a source is supplying, then the current will be from the current will go out from the positive terminal. So here power delivery will be positive. Whereas if I consider something like this, so current is entering the voltage source, which means it is taking the power. It is not delivering the power. So power will be negative. So when someone asks the power delivered, then you have to see whether the current is entering or leaving. If the current is entering, then it is power entering, means it is taking power. If the current is leaving, means it is delivering power. So in this case, the power supplied by this 5 volt is 5 into I1 and I1 is positive. So we'll get 5 into 3.1. So it is 15.5 watt. Similarly, you have to check the voltage across this current source. Again, current source, you have to remember, if a current is being as a source, then the polarity should be like this. So how will the polarity look like? The polarity will look like something like this. So the polarity will look like something like this. So this terminal is positive and this terminal is negative. And if you found this voltage, we got this voltage is at a negative 57, right? So we got that it is at a negative 57. So which terminal is positive? This terminal is positive, this terminal is negative. So the current source is also supplying the power. So power supplied by the current source 5 ampere is the voltage across it, which is 57 volt, and the current it is supplying. So 5 7 25, 275 watt. So the current source is supplying more power than the voltage source, and that's how you calculate. So when you are asked what is the power supplied by sources, you need to keep in mind two things. One is the voltage current values that are being supplied by the voltage or current source, and the direction of the current or the voltage or the polarity of the voltage. So you have to see whether it is supplying or whether it is taking. Sometimes they ask in the question, what is the power supplied by a source? But in fact, if it is taking the source, I mean, in fact, if it is taking the power, then you have to put a minus, because if it is taking 15 watt power, then it is delivering minus 15 watts. So it is just a polarity change. So that you need to keep in mind. So if they twist that question, then you have to put the minus in your answer, else it will be considered as a wrong. So you have to be careful with this polarity. So I hope this is clear.
Yes, sir.
Okay,
Yes, sir,
so
clear.
Yes, sir.
okay, then you try to solve more problems and try to do it by hand rather than looking at it and thinking that this can be solved in this way. It is highly advisable for you to solve all the questions. Then it will be helpful in your exam. You will not do more calculation mistakes. And as this video will be uploaded, you are free to go through this video at any time. If you have any questions, you can mail me, or you can mention in the comment box of that YouTube video. I will be trying to reply it, address all the comments. And yeah, we will meet in the next week for week 3 content. And tomorrow is also there is another session. You are free to attend that session also. Yeah.
Yes, sir. Thank you, sir.
Okay then. Yeah. Thank you. Thank you so much. We'll
Thank you,
meet
sir.
in the next
Your
week.
teaching
Good
math
night.
is best.
Yeah. Thank you. I hope I'm helpful to all of you. I'll take feedback from you every week, and I want this to be more interactive. Then only I'll be motivated, and you'll also be learning so many things. Yeah, so we'll try to learn from each other, and I'll give my full efforts to help you people also. Yeah, see you in the next week, and all the best for your
Thank you,
week
sir.
3 assignment. Thank you. Good night.
Thank you, sir.
Thank you, sir. Good night.
Good night.